Today we have Chen Davidson that will present his PhD talk. The PhD was done with Alon and Alon, that you all know. And please go on.
So, hi everyone, I'm Chen. I will talk about sulfur isotopes of carbonyl sulfide. This work was done under the supervision of Alon Angert and Alon Amrani, with collaboration with Cynical Leonards from the University of Oldenburg and Yasmina Vidani, a master student in our lab. So carbonyl sulfide, or COS, is the most abundant long-lived sulfur gas in the troposphere, with a lifetime of a few years. But its concentration in the atmosphere is fairly low. It's a trace gas in the concentration of about 0.5 parts per billion, which is 1 million times lower than CO2. The reason we are interested in COS because it's a major source for stratospheric sulfite aerosol, which increase Earth albedo, and by that having a cooling effect on Earth. There is a flux. This work was done by Chen and Davis. There is a flux from the troposphere to the stratosphere, and then it can undergoes photolysis and oxidation with O and OH to create SO2, which then becomes sulfite aerosol. The other reason we are interested in COS is because it's a promising proxy for gross primary production, which is the removal of CO2 from the atmosphere by terrestrial plants. So basically, when plants open their stomata, COS enters to the leaf and undergoes a rapid and irreversible hydrolysis. And we can use this flux to estimate plant stomata opening and then upscale it to gross primary production. You can see over here by Ma et al. The COS flux globally, and you can see the big uptake of COS in the blue colors over forests. And in the red colors, it's the emission by biomass burning. And this work by Asaf et al. Can show over an entire ecosystem, over a forest, the nice correlation between the COS flux in uptake by plants in the y-axis and then the CO2 uptake in the x-axis. So we can use it as a proxy for gross primary production. And this work by Campbell et al. Show the different sources and sinks of the COS. And you can see the largest source is emission from the oceans. And you can see this huge uncertainty in teragram sulfur per year, between almost nothing to a huge source of 1.2 teragram sulfur per year. The second major source is the industry or anthropogenic emission, and the largest sink, plant uptake, and again you can see these huge uncertainties. And what Campbell did, very nice work, they measured COS in air that capture in firm, and they did a reconstruction for the last 100 years. So they had models for the emission by the industry and the emission by the ocean, and by that they calculated the uptake of COS by plants, and then they calculated the gross primary production in the last 100 years. And they showed a growth in GPP, but it's in the range of 5% and 34%, which is, of course, a huge uncertainty. But this is a very interesting work. And as I said, the problem is that these huge uncertainties regarding the COS budget limits the use of COS in GPP and stratospheric sulfate aerosol models. And what we want to do, our main goal, is to develop and improve global COS budget based on sulfur isotopes. What we measure in our lab is the two common isotopes, 32S and 34S, and then we standardize using the delta 34S notation. And from now on in this talk, whenever I'm saying isotope, I'm talking about delta 34S. And this leads me to the thesis structure. The first chapter is a method development of sampling and measuring COS, CS2, and DMS from the oceans, their isotopic values. The second chapter was published in 2021. That's focused on the entire tropospheric budget using an isotopic mass balance. And then the other chapters kind of go deeper into each source and sink. So the third chapter was also published in 2022, and it focused about the uptake by plants. And then there are chapters 4 and 5, also they go deeper into the oceanic source. But because of the time limit, today I will talk about chapter 2, 4, and 5. So let's start with chapter 2, the tropospheric COS mass balance. So our main goal is to constrain the tropospheric COS budget using sulfur isotopes of COS. And more specifically, to do that, we need to measure the isotopic signature of the troposphere, anthropogenic emissions, oceanic emissions, and the uptake by terrestrial plants. And to do that, we also need to assume that there is a steady state between emissions and sinks, that each major component has a unique isotopic signature, and it's okay to neglect smaller sources and sinks. And then we can use this equation. If we take only the anthropogenic and oceanic emissions, assuming steady state, it should be equal to the uptake by plants. And then we multiply each component with its isotopic signature. And then we can calculate the relative contribution of each source. We used sulfur isotope analysis of atmospheric COS using a pre-concentration system, using a 3-liter sample. We concentrate the sample, we transfer it into a gas chromatograph for the separation of the different compounds, and then via a transfer line, we measure it on the multi-collector ICP-MS for isotopic analysis. This is how the system actually looks like. And currently there are only, as far as I know, 3 labs in the world that actually can do such measurements, and we are one of them. To measure COS and other compounds in the ocean, we use an equilibrator. Basically, we pump seawater into this chamber. The water constantly replaced, but the headspace is stuck inside, and then there is diffusion of the gas, and eventually we reach a steady state in which the headspace actually should be similar to the gas in the aqueous phase. Then we sample this gas for preservation in these 3-liter canisters, and we can measure it on the multi-collector ISO-PMS in the same way we measure air samples. As far as we know, currently we are the only lab that measure these volatile organic COS and CS2 in the oceans, their isotopic values. And DMS was measured previously in other works. This is how the equilibrator looks like when it's open, and you can see the spray of seawater. And our last method in this chapter, we use the plant chamber. Again, it's a closed chamber. We insert a plant inside. We constantly monitor CO2 in the chamber, and then we can sample after a certain period of time. We sample the gas into a 3-liter canister, and again we can measure it in the same way like air samples. This is how the chamber looks like. These are the results. At the time, it was the largest database of atmospheric COS measurements of sulfur isotopes. You can see in the map here the different locations around the world where we sampled. Most samples, of course, are from Israel. And you can see in the y-axis sulfur isotopes values. And it's a killing plot, so in the x-axis, it's 1 divided by the concentration. And we have 2 groups of samples. On the right side, there are clean air or normal air samples that the concentration is between 400 and 600 ppt. And then on the left side, we have samples that are suspicious because they have high concentrations, and they are probably influenced by high anthropogenic emissions, which are quite local. These air samples are not fully mixed with the atmosphere, and we use these air samples in a killing plot to estimate the isotopic signature of the source, that anthropogenic source. This is given by the intercept with the y-axis, and we calculated it to be 8 per mil. There is another group, Japanese group, that did something quite similar in 2020, and they calculated isotopic value of the anthropogenic emissions to be 4.7 per mil, which is quite similar to what we measured, and it's quite amazing because their air pollutant is mostly from China, from the Ryan industry, which is a very different source than the one we expect to have here. Then we want to have a look on the uptake by plants. And you can see on the right side, in the blue line, the concentration in the y-axis and the season in the x-axis. And you can see this really nice seasonal trend, which is well known. It's measured, these trends in COS concentration was measured many times before. And this is because of the plant uptake during summer in the northern hemisphere. But this was the first time that we showed a similar signal in isotopic values, in which you can see that during the summer, the isotopes become heavier, and this is because the plants prefer to take the lighter isotopes. And then to complete this, we did the plant chamber experiments, and this is a Rayleigh distillation plot. Basically, the slope gives us the fractionation of the uptake, and you can see that the plant uptake fractionation is minus 1.9 per mil, meaning that the plants prefer the lighter isotopes and the remaining air become heavier, which we also see here. And the last part of our measurements in this chapter was oceanic emissions, but at the time we didn't have any oceanic emissions, so we only had samples from the Red and Mediterranean seas. But for at least first estimations, we wanted to use it. So we measured COS in the value of 13 per mil, and CS2 and DMS, which are very important precursors of the COS. CS2 in the value of 15 per mil, and DMS in the value of 20 per mil. And this value of 20 per mil also agrees with previous work done by Amrani at 2013, which gave us additional confidence that this method works. And then, using global estimates from Wellen et al. Of the different fluxes, we calculated the isotopic signature of the oceanic source, even though we don't have any oceans here. So, to summarize the different component of the mass balance, tropospheric COS is in the value of 13 per mil. The anthropogenic source is 8 per mil. Plant uptake is about -2 per mil. And the oceanic source is about 15 per mil. Now we can plug all of these values into the equation of the isotopic mass balance, and we calculated the anthropogenic source to be 40 plus minus 70% of the budget of the source, and the oceanic source 60 plus minus 20%. Now, it may seem that there are still quite large uncertainties, but this is an improvement than the previous estimates. If we take the most recent inventory of the industry source, which is, as you can see here, a bit better known than the oceanic source. But we want to even improve our knowledge about the COS budget, and we want to reduce uncertainties, so we need a more complex model. But before we can do such a model, we need to better know all the different components and all the different fractionations in the COS budget and destruction and production pathways. So what the next chapters will focus are on these specific production and destruction pathways. So in the future, someone else maybe could do such a model. So as I said previously, chapter 3 focus of the plant sink, but I will not talk today on this chapter. And chapters 4 and 5 focus on the marine source. Chapter 4 will focus on the open ocean, and chapter 5 is of things that are associated with the sediment. I will just say that chapter 3 was published in 2022, and we updated the fractionation from minus 1.9 to minus 2.3 per mil. And now I will talk about chapters 4 and 5 that focus on the oceanic source. So since the Red and Mediterranean seas, we sampled and measured many more samples. You can see here the different locations, the Wadden Sea, the North Sea, of course, Mediterranean and Red Seas, Atlantic Ocean above the sea shelf next to West Sahara, and this north to south cruise across the Atlantic Ocean. And you can see the huge variability in isotopic values in the y-axis, also in concentrations, but mainly isotopic values. So we can be quite confident now that we cannot use just an average from the Red Sea and Mediterranean seas to say something about the oceans. We need to do a much more thorough work. And what we want to do in chapters 4 and 5 is to identify the different processes that control this big variability in the ocean. As I said, chapter 4 will talk about the open ocean, and chapter 5, sediment as a case study in the Wadden Sea. So just a short introduction about the open ocean. The main source of COS in the open ocean is dissolved organic sulfur that undergoes photolysis and creates COS under UV light. We have an additional source, non-photochemical production or dark production, and no one basically knows what's going on there. Some estimate it's a physical process, some estimate it's a biotic process by bacteria. No one knows. There are two main sinks for COS in the ocean. One is hydrolysis. This work was done by Yasmina Vidani, and she calculated the fractionation caused by hydrolysis to be minus 2.6 per mil in the ocean. And the second sink is the degassing from the ocean to the atmosphere. In our methods, we did photo production experiments. We used water in pH 8 using cysteine, an amino acid, as the precursor. This amino acid is well known to produce COS under UV light. But of course, no one previously measured the sulfur isotopes. And we used humic acid as the photosynthesizers. Humic acids absorb UV light, create radicals that attack the amino acid and create COS. And the second method to estimate what's going on in the open ocean, we used the data from the open ocean, from this cruise, which Yasmin was brave enough to go from Germany all the way to Cape Town to collect the samples. So the results of the photo production experiments show isotopic equilibrium after about 22 hours under UV light, in which the produced COS became heavier in 3.6 per mil from the source. But we must remember that also in the bottle, not only in the ocean, we always have hydrolysis. So we must take into account the fractionation caused by hydrolysis, calculated by Yasmina Vidani. And if we assume a quasi-steady state between production and hydrolysis, we can calculate the fractionation caused by photoproduction to be around 1 per mil. This is the data we measured from the Atlantic Ocean. You can see in the blue line continuous measurements of COS concentrations here in the y-axis, and on the other y-axis in the orange you can see the isotopic values of discrete samples that we took along the cruise. And what you can see here, first of all, it's very obvious that the COS concentrations show a very strong diurnal cycles, and this is because of the very rapid photoproduction during daytime, and then no photoproduction during nighttime, and the hydrolysis works all the time. So we get these really nice diurnal cycles, and this is well known. But here we show for the first time that also sulfur isotopes show very nice diurnal cycles, in which during the daytime sulfur isotopes of COS become heavier, and then during nighttime they become lighter. So we divided the samples into two groups: sample taken during dawn, just before sunrise, and sample taken in the afternoon at the peak of the concentration. So at maximum concentration, we get an average value of 18 per mil, and in early morning show an average value of 14 per mil. And if we exclude this one measurement, then this is a very significant difference. And we can use it to do different calculations. So, we still don't know what is the isotopic value of the source, all the different amino acids and other organic compounds in the dissolved organic sulfur pool that create COS. So if we assume that there are only two things that are controlling at the peak concentration the isotopic value, the fractionation caused by photoproduction and the source, because we know that this is a much, the rates of photoproduction are much higher than the other processes. So we can calculate it, the source to be in the range of 15 to 18 per mil. This agrees with Phillips et al. 2022, which they measured the isotopic values of the bulk DOS pool and not only the specific molecules that produce COS. And during dawn, early morning, if we assume steady state between dark production and hydrolysis, because it's during the night we don't have photoproduction, so we can calculate the fractionation caused during dark production to be in the range of -2 to -7 per mil. And this may indicate that the dark production is promoted by biotic processes, by bacteria, and not by a physical process. So, to summarize, COS from the Atlantic Ocean show a mean value of 17 per mil. The fractionation during photoproduction calculated in our experiments from cysteine show a value of 1 per mil. The source in the DOS pool show probably has an isotopic value in the range of 15 to 18 per mil. Dark production was calculated to be in the range of -2 to -7 per mil. And the hydrolysis fractionation calculated by Yasmina Vidani to be -2.6 per mil. So we're starting to understand the different processes controlling the different isotopic values in the open ocean. But, of course, we need a new model that takes into account all these fractionation together with the rates of the reactions. Chapter 5 will focus about additional things that are going on in the sediment. So now we're making the system a bit more complicated. This part you already saw in the open ocean, and now we have additional processes that may affect the isotopic value of COS in the ocean. So in the sediment, because of the low oxygen rates, some bacteria use sulfide as the electron acceptor instead of oxygen in dissimilatory sulfate reduction, and this process is associated with a very strong fractionation. So they produce H2S, which has a very low negative isotopic value. And then this H2S can further react. It can produce directly COS if it reacts with the CO, and then this COS can leak to the water and mix with the other COS, and also it can react with many organic compounds and create a different pool of dissolved organic sulfur, that if this pool migrates and mixes with in the open ocean, then we have another signal of isotopically light COS. And to check this phenomena out, we sampled in the Wadden Sea. It's a very unique setting. It's almost like natural lab. The Wadden Sea in northern Germany is basically made out of sedimentary mud flats that are stuck between northern Germany and this row of islands. And then to the north, you have the North Sea. And the sediments here are full with organic material because of all the sediments that big rivers in northern Europe bring here. And then you have very strong currents of the North Sea. So we all the time have this mixture. During low tide, pour water from the sediments just flow out into this gorge to the North Sea. And during high tides, water from the North Sea enters, and we have this constant mixture. So we sampled there, and this is again a killing plot for COS isotopic values. You can see in the y-axis the isotopic values, and 1 divided by the concentration in the x-axis. And you can see that we have a intercept with the y-axis of -4 per mil. This is a very different value than what we saw in the open ocean of +17 per mil. And what another interesting thing is that we can see also here a very strong diurnal cycle in sulfur isotopes. But this trend is opposite. In the open ocean, during daytime we saw heavy isotopes, and here during daytime we see very negative isotopes. And what we assume is the reason is that the major process here is not the direct production of COS from H2S, but the production of dissolved organic sulfur, many precursors that migrate to the water column, and when they are photooxidized, they produce isotopically light COS. But during nighttime, what controls the isotopic value is the mixture between the remaining COS and the mixture with the COS that comes from the North Sea. And now let's have a look again at all of our samples, marine samples. And we want to say that not only in the Wadden Sea, these are the values from the Wadden Sea, not only in the Wadden Sea we have this effect of the precursors that migrate from the sediment to the water. We think we can see this phenomena all over the world, in which we have samples that represent the open ocean. They show heavy isotopic values, and then we have intermediate samples, for example, the Mediterranean Sea or the North Sea, that are more associated with the sediment because they are closer to shore and shallower water. And then we have the Wadden Sea, which is almost like a lab experiment of what's going on in the sediment. And what a very interesting thing, you can see that even at the Atlantic Ocean, in water depth of hundreds of meters, but above the sea shelf here, we have slightly lighter isotopic values than the real open ocean. So maybe this phenomena of COS that is associated with the sediment can affect tens of kilometers away from shore and in water depth of hundreds of meters. So, summary and conclusions. COS from the Wadden Sea indicates unique source of -4 per mil. I didn't talk today about CS2, but it also shows a unique isotopic value of -12 per mil. During the diurnal cycles indicate the formation of photoactive precursors that migrate from the sediment to the water and produce isotopically light COS and CS2. And these precursors may also have an effect far away from shore above the sea shelf. So that's chapter 5, and I want to summarize the entire talk. So sulfur isotopes can effectively be used to constrain the tropospheric COS budget. The isotopic mass balance indicates a contribution of 40 plus minus 70% of the anthropogenic source and 60 plus minus 20% of oceanic emissions. Sulfur isotopes of marine COS show large variability, and if we want to further reduce uncertainties regarding the COS budget, then we can measure and calculate all the different processes of COS production and destruction, and then in the future we can create a much better model to constrain the COS budget. I want to thank you for your listening, and a special thanks to my supervisor, Professor Alon Angert and Professor Alon Amrani, and collaborators, Sinika Linertz and Yasmina Vidani.
Questions?
Very cool talk.
Thanks.
So, have you considered fractionation during the degassing of COS from the water to the atmosphere? Is that a thing?
Yes. We did some experiments that show that for COS it's about half per mil. And Alon Amrani did in the past experiments for other compounds, and they all show something in the range of between 0 to half per mil, so it's not very significant. Yes.
You show fractionation in hydrolysis and fractionation in uptake by vegetation, and they seem pretty similar. Is this the same enzyme that is involved in both processes?
No. In the ocean, it's a physical process. COS reacts with OH or with H2O, depends on the pH. And in the plants, there is an enzyme called carbonic anhydrase. And I didn't talk about this chapter that focuses on it, but basically the enzyme have a much stronger fractionation, but then you have also the diffusion component. And the combination between diffusion and enzymatic components cause this, by mistake, this quite similar fractionation.
Another one. So, it seems that, I mean, the fractionation in the sediments for sulfides or reduced sulfur compounds is huge. It's like tens of per mils. And I was wondering, looking at your data, how much of, like, did you try to quantify the flux, or how much flux do you get of, from the sediments to the water?
So it's really complicated. Other works, there are other researchers working on this, and it's a big unknown because there are quite a lot of works done in the Wadden Sea and North Sea because it's in Europe. But you have many other environments that have the potential to have this huge contribution from the sediment. And no one, there's not a lot of works. It can be that even part of the COS emissions that are associated with anthropogenic emissions in China, maybe it also associated with the big rivers in Southeast Asia that discharge this organic material. But there's not enough of work done, and again, we are the only ones that measure sulfur isotopes of COS in water. So all other works done only on concentration.
So
So there's still a lot of work on what happened with the sediments for the next students. There's a funded proposal and we're also working on the next one.
You touched it briefly. Can you summarize or give us a few evidence that support biological production in the ocean?
So I think that the negative fractionation, usually biologic processes are associated with stronger negative fractionations, and the photo production showed a small and positive fractionation. So I would assume that if it's a physical process, it shouldn't be so different from the photo production, because in both ways it should be radicals that react with the source. So yeah, but it's more of a clever guess. There is a lot of other work to do here, but that would be the job of another student.
Okay, so before we go, since we don't have our almost weekend gathering today, then Monty asked to give the 60 seconds in Hebrew here.
נעבור לעברית. אוקיי, אז עכשיו אנחנו נמשיך במנהג שלנו. אין היום את ההתכנסות בחדר הסגל. יש לך 60 שניות בעברית ברורה וצריכה להסביר את מה שאף אחד פה לא הבין כאן עד עכשיו.
אוקיי, בסדר.
תתחיל.
תודה. אז קרבוניל סולפיד או COS הוא מעניין את הקהילה המדעית משתי סיבות. הוא מקור חשוב לאירוסולים של סולפט בסטרטוספירה שמחזירים את קרינת השמש ומקררים את כדור הארץ. וסיבה נוספת, הוא משמש כפרוקסי, איזשהו מדד שבעזרתו אנחנו מעריכים כמה פוטוסינתזה צמחי יבשה עושים, וכמו שכולכם יודעים, לצמחי יבשה יש גם השפעה ענקית על האקלים של כדור הארץ. אבל יש אי ודאות גדולה בקשר לגודל של המקורות והמבלעים של COS, ואם אנחנו לא יודעים כמה COS נוצר וכמה נצרך, אז זה קצת קשה לנו לעשות מודלים כאלה מורכבים על אקלים. אז אנחנו משתמשים באיזוטופים של גופרית כדי לקבל מידע נוסף על כל המקורות והמבלעים של COS, ובעזרת האיזוטופים להקטין את השגיאה ואי הוודאות בקשר לגודל של אותם מקורות ומבלעים.
60 שניות.